Hey everyone, it's Dr. C. I'm going to try to make this pre-lecture really quick. I'm just going to look at the 5 most missed questions on the exam. I was going to do 4, but then there were questions 3, 4, and 5 are really close in the percentage of students who got those right. So let's start with number 5. This was one of the 5 most missed questions. So the wording of this question maybe could have been a little bit better, but it said consider each choice individually, which is always true for a spontaneous process. And the only thing that are always true, if you look at them individually, second law of thermo, delta S universe positive. Another way to say that is entropy increases in a spontaneous process. All right, so that's one way we determine spontaneity. The other way is with delta G, the free energy change. All right. Now, what is the sign of the free energy change that predicts spontaneity? Yeah, it's actually negative. Okay. So if we had a negative delta G, that would also indicate spontaneity. Those are the two things. Second law of thermo, entropy change of the universe, and the free energy change. Those by themselves will tell us whether a process is spontaneous. Since we have the wrong sign of delta G, the only one that is correct is delta S universe. Now be careful. We know this is exothermic for number 5. Yes, exothermic reactions tend to be spontaneous, but not always. Okay? We tend to think of reactions that lead to an increase in entropy, delta S of the system, delta S of the reaction. We tend to think of those as spontaneous, but not always. So again, just by itself, delta S universe, delta G, if it's negative. Okay? All right, so that's number 5. I kind of figured I'd see number 6. We've talked about this type of problem. Students always struggle with these. Okay? So a couple things to think about. If you're going from solid to liquid to gas in that direction. Delta H, delta S, positive and positive. To melt a solid, we have to add heat, endothermic. When we go from, same thing for liquid, to evaporate a liquid or boil a liquid, we have to add heat, endothermic. When we go from a solid to liquid, energy is more dispersed. That's an increase in entropy, positive. Same thing, liquid to gas. A gas, energy is much more dispersed than the liquid, both positive. If we turn that around, gas to liquid to solid, delta H will be negative, delta S will be negative. Okay? To get a gas to condense, we have to get energy out of that gas. All right, so we have to get energy out of that system that's exothermic. Same thing to get a liquid to freeze. We have to get energy out of that liquid. Slow down the motion of those liquid molecules. All right, and then again, gas to liquid, energy is much less dispersed in the liquid than a gas. Energy is less dispersed in a solid than a liquid. That's a decrease in entropy. So these are our 2 temperature-dependent situations, positive, positive, negative, negative. So now we have this situation, liquid to solid. We know delta H, well, that almost looks like a smiley face without the smile. We have negative and negative. So our only possible choices are A and C. All right. So the next question then is, what is delta G? Is it spontaneous or not? Is this freezing of sodium liquid, is it going to freeze and go from liquid to solid? Is it going to happen at that temperature? And I really tried to help you out. Here's the normal freezing point of sodium. 150 degrees Celsius, I even stated, it's a temperature above the freezing point. Okay? So we're above the freezing point. Is that liquid going to freeze? No. Not spontaneous above the freezing point. All right. Now, if I change this temperature to 50 Celsius, okay, not 150, but 50 Celsius, now we would be below the freezing point. That liquid would freeze. But in this case, it's not spontaneous. The correct choice is A for this version of the exam. Okay, so not spontaneous, delta G is positive. Okay, think through these. So for these phase changes, delta H and delta S are fixed depending on which direction you're going. And then you have to look at the temperature to decide, is that process spontaneous at that temperature? And that will tell you whether delta G is negative or positive. All right. So 5, 6, 7, we were on a roll here because these were 3 of the most missed questions. So let's look at this one. Delta S universe. So here we finally have a calculation. So the first thing I would do is say, we want to calculate delta S universe. How do I do that? And so the first thing I would look up, if you don't remember this, look on the equation sheet. Delta S universe is delta S system plus delta S of the surroundings. Okay? Well, what do we know? Do I know delta S of the system? Do I know delta S of the surroundings? No, I don't know either of those. I have delta H of the system, all right, but I do have standard entropy values. So then I start thinking, oh, standard entropy values, what can I calculate from that? And that's how I can calculate delta S of that system. Okay. Now remember, we do use reaction interchangeably with systems. So delta S of the reaction, delta S of the system. All right, so then I'm like, okay, yeah, I can get to that. What about delta S of surroundings? Oh, well, I might remember an equation we talked about and how heat flow affects the surroundings. But if you don't, look on the equation sheet and you should find another equation. Delta S of surroundings is equal to negative delta H of the system divided by the temperature. Okay, so now I have my delta H of the system. I can plug that in there. I can plug in my temperature in Kelvin and solve this problem. So quite a bit of work for this problem. This was not a short problem. And I'm going to need a little bit more space. So let's do delta S of the reaction first. Delta S of the system. We can calculate that by summing together the standard entropy values of the products, then subtract off the standard entropy values of the reactants. Substituting in, don't forget to multiply by the coefficients. My reaction is now off screen. So 2 times the value for NO, which is 210.8 joules per Kelvin mole. All right, plus O2, we only have 1 mole of O2, times 205.2 joules per Kelvin mole. All right, and then we subtract off the reactants, 2 moles of NO2 at 240.1 joules per Kelvin mole. So what do we get for that? Okay, let me... Okay, so I end up with 146.6. So maybe I typed something in wrong. So I think it comes out to 146.2. Let's see if I wrote something down wrong. 210.8, 205.2, and 2... Oh, maybe I just, okay, so I got 146.6 joules per Kelvin, positive, okay, and this should be positive because we go from 2 moles of gas to 3 moles of gas, so that should be more dispersal of energy and increase in entropy. So we have that part. Now we have to calculate the delta S of the surroundings part. And this is where we have to be a little bit careful. Because of our units. We want to end up with joules. Delta H is in kilojoules, 113.1 Now watch that negative sign. Okay, so there's a negative there. Our delta H was positive, correct? Yes. So we have a negative 113.1 kilojoules. We need to convert that to joules. So kilo means 1,000. Temperature was 25 Celsius, which is 298 Kelvin. This comes out to negative 379.5. I think I'm doing something wrong here. No, that's right. Somehow I had in my mind that this answer was there for some reason. I guess I didn't do that. All right, so there we have it. We have delta S reaction. We have delta S of the surroundings. Again, delta S reaction is delta S of the system. All we have to do is add those together, right? Delta S of the universe is delta S system plus delta S of the surroundings. So just add those together. So our delta S of the universe, delta S of the sys, 146.6 joules per Kelvin, plus a negative 379.5, which is delta S of the surroundings. And you should get negative 232.9 joules per Kelvin, which on this version exam was choice E. Sorry about that. That was not the smoothest calculation, but I did get it right, I think. So the other thing I wanted to ask in this question, but I did not, is this reaction spontaneous at that temperature? No. Negative delta S of the universe, that would not be spontaneous. Okay. Now this reaction could be spontaneous because it does have a positive delta S. It does have a positive delta H. That's going to be temperature dependent. At this temperature, it's not spontaneous. All right. (15) So in this one, you are given a rate law. I would look at that. Okay. And it's asking about the rate constant. What would alter the value of the rate constant? So the first thing I'm thinking, okay, I have a rate law. The rate constant is part of that. But rate constant, what does that mean? So right away I start thinking, well, it's typically a constant for a reaction. But something changes it, and what is that? And you might know that right off the bat. It's a constant for a reaction, constant at a given temperature. If we change the temperature, the rate constant will change. So the correct answer, so you might have enough knowledge, and you should know this, it's a constant for that reaction at a given temperature. The correct answer is changing the temperature, decreasing the temperature. Okay. Now, what about all the other things there? Okay. Well, look at C. This is also temperature. Measuring the rate constant again after the reaction had run for a while at constant temperature. If we keep the temperature constant, K will stay the same. So that's out. Right? What about changing the concentration? All right. I increase the concentration of A. What changes? Is it the rate constant? No, it's the rate. This is a first order. If I double A, the rate doubles. If I triple A, that's like an insurance company. If I triple A, then the rate triples. That's what first order means. So changing the concentration changes the rate. It does not change the rate constant unless the temperature changes. What about decreasing the concentration of B? Same thing. Decrease concentration of B, the rate changes. The rate constant depends on the temperature. It's a constant for that reaction at a given T. All right. Make sure you know that. You will probably see that if you take the retest. You'll probably see it on the retest. And the last one was the last problem on this exam. So we're reading through this problem. We have the temperature. That's okay. The temperature really just tells us that if we're given a rate constant, that's the rate constant at that temperature. Bing, that's the first thing I notice. First order. That's important. Rate constant, that's K. Starting concentration, oh, that's my initial. What will the concentration be after 2 hours? Oh, I want to solve for concentration at a later time. 2 hours, that's time. Okay, pick out the information, look at what we have. We have rate constant, we have initial concentration, we have time. We want concentration at a later time. What equation tells us how concentration changes over time? And that is the integrated rate law. How does concentration change over time? The rate law, rate is equal to K times concentration, that tells us how concentration affects the rate. But if you want to know how concentration changes over time, you need the integrated rate law. This is first order, so we need the first order one. Look on the equation sheet if you do not know this equation. There are two different forms that you would find on the equation sheet. I think this one is easier if you're solving for concentration. So let's do that. Plugging in. Now this is where a lot of you probably went wrong. You have to write units. It's really essential because if you notice, once we start writing our units, and I know students don't like to write units down, our rate constant has time in minutes. Our time is in hours. Those have to be the same. So 2 hours, let's convert that to minutes. 2 hours, 60 minutes in an hour. It's going to be 120 minutes plus the natural log of the initial. Oops, I can plug the initial in, can't I? Sure can. What is it? 0.0314. Sorry about that, I'm out of room, and that's molarity. Let's do the calculation on the right-hand side of the equation. And I get a negative 4.23 on the right-hand side. We still have a natural log term on this side. Okay. So how do we get rid of that natural log? Yep, e to the x. And so this will just give us, I'm out of room on this page, concentration, e to the negative 4.23. And I get 0.0146 molar. Okay. Now, it's a good idea to double check to see if at least we're in the right ballpark. Okay. So, for example, there's one answer that can't be possible, right? We start at 0.0314. We would not go up to 0.0677. All the others look at least reasonable because they're less than what we start with, so that's good. If you had time on this, one thing you could do to double check, to have some idea if you wanted to see better if you're in the ballpark, is to calculate the half-life from the rate constant. And see how much time it takes that to be cut in half. Because that concentration in half is going to be what? 0.0157, which is actually close to that, to our final answer. So if you see that the half-life is close to 2 hours, that would tell you that you're probably you're probably right with this one. So anyway, it's 0.0146. All right. So I think it's always a good idea to go back and review an exam after you've completed it. I know some of you did really well on this exam. Some of you need to do more work. So at least all of us are going to go back and look at some of these questions. This is kind of a beginning of a recording for me for this exam, because I will record the rest of these problems for those of you who are trying to prepare for the retest. That probably will not show up until Friday. Okay, so I will just add to this recording. So it'll be a little disjointed because there will be these 5 problems, and then I'll go back in the remainder of the recording and do all the rest. Hope that makes sense. Anyway, I will see you in class on Thursday if I don't see you at office hours on Wednesday. All right, take care. Hey everyone, it's Dr. C. Happy Friday. What I'd like to do in this recording is go through probably about 10 of the Exam 1 problems to help you prepare for the retest if you're going to take that. Now, in the pre-lecture for Thursday, I did record the 5 most missed problems. So I'm going to append those at the end of this recording. So I'm going to skip some of the problems. But I'll do about 10 now, get this up on Friday, and then I'll probably finish it up on Saturday. Okay, so I wanted to at least get part of this up there. So let's go ahead and start with problem 1. Which of the following has the smallest standard entropy? All right, so make sure you know in general that entropy increases in the order from solid to liquid to gas. All right, so that's an increase in entropy this way. Okay. Now the size of the molecule will also come into play. Smaller molecules will have less dispersal of energy, a lower entropy. Larger molecules, the energy will be more dispersed in that molecule. There will be more bonds stretching and bending. There will be more vibrations and rotations and all sorts of things. Okay. So right away, we're looking for the smallest. So my first thought is I'm going to think solid. So then I look, here's a solid, here's a solid. Okay. Clearly, glucose is a much larger molecule, more bonds, more motion, more dispersal of energy. That's going to have a significantly larger entropy than the much smaller atom of carbon. Okay. So the correct answer is B, the smallest standard entropy. All right. Problem 2. Which response includes all the following that are accompanied by a decrease in entropy? So we're going from more dispersed energy to less dispersed. Or we can simply think of from more disorder to more order. All right? So again, solid liquid to gas is an increase. If we go the other way, gas to liquid to solid, that would be a decrease. So look at number 1, gas to liquid. That is certainly a decrease. All right. Let's go to number 2. 2H2 plus O2. So that's 3 moles of gas to only 2 moles. So we're decreasing the number of gas particles. That is certainly a decrease in entropy. All right. So a lot of reactions, you can look at just the amount of gas you have on each side. If there's a decrease in the amount of gas particles, energy is quite dispersed in a gas because there's random motion of gas particles. We've cut our particles by 1/3. We've gone down from 3 moles to 2 moles. All right, let's jump to 4. What does this represent? What kind of reaction is this? Yeah, this is a precipitation reaction. So we're taking dispersed ions in solution, hydrated by water, they're in motion, and we're forming this ordered crystalline solid. That is certainly a decrease in entropy. Okay, so I at least know that it's 1, 2, and 4. The last one we'd have to check is 3. This one's a little tricky because it's N2 to N, but again, just look at moles of gas. We're going from 1 mole of gas to 2 moles of gas. I am doubling the number of gas particles. Okay, twice as many particles zipping around and colliding and all of that. That's going to be much more disorder, much more dispersal of energy. So that one is an increase, and that's the only one. So 1, 2, and 4 are all decreases. The correct answer is A. Okay. Now this is one version. I think this is, what colors? The white version and the yellow version, I think. I'm not sure. Anyway. All right, next one. Delta H of a system is exothermic. Then what does that do to the entropy of the surroundings? So you have to know what exothermic means. Exothermic means heat is released, or maybe a better way to think about it is heat flows from the system out to the surroundings. Okay, so we're having the transfer of thermal energy out of that system out to the surroundings. So we're putting this extra kinetic energy, this extra thermal energy out to the surroundings. What that's going to do is that's going to cause more motion in the surrounding molecules. Okay, more motion, energy is more dispersed, more disorder, however you want to think about it. that heat, that thermal energy flowing out of the surroundings is going to increase the entropy of the surroundings. Okay. Conversely, endothermic reactions are going to absorb heat from the surroundings, pulling thermal energy out of the surroundings. That would decrease the entropy of the surroundings. All right, so think about that. All right, number 4. We have a process, negative delta S of the system, and a positive delta H. So you have to know what the sign conventions are. Positive delta H. What is that in terms of heat flow, endo or exo? That's endo. Negative delta S, increase or decrease in entropy? Yeah, negative, decrease. Okay, so the way I like to think about these are in terms of favorability. What's favorable for heat flow? Okay, when we think about spontaneous reactions, what are most of those reactions in terms of heat flow? In terms of spontaneous processes, entropy, what's favored? Okay, what's more likely to lead to a spontaneous process? Okay, and both of these are unfavorable. Okay, reactions that release heat tend to be spontaneous. Not always, and there are endothermic reactions that are spontaneous, but in terms of heat flow, reactions that release heat are favored. Reactions that lead to an increase in entropy are favored. So both of these are going the wrong direction. They're both unfavorable. So that type of process is not spontaneous. Okay, so make sure you can go through all the possibilities, for delta H and delta S. Negative, positive, always spontaneous. This one that we saw, positive, negative, not spontaneous. And then we have the two where we have one favorable, one unfavorable, positive, positive, or negative, negative. And these two will depend on temperature dependent. So make sure that you can go through those 4 possibilities. Always spontaneous, both favorable. Not spontaneous, both unfavorable. One of each. Here we have a favorable entropy change, positive. Here we have a favorable enthalpy change, exothermic. Those will be temperature dependent. All right. 5 was one of the most missed problems on the exam. So that was already done in the pre-lecture. Again, I'll attach that at the end of this. So once I get done through maybe 10 problems, I'll just clip that on. So it'll just jump into that. So 5 was one of the most missed. So was 6. So was 7. So those are going to be done in the next video. Let's go to 8. All right. Delta H, heat flow. No, you should look at that and go, boom, exothermic. That's the amount of heat that's released for that reaction as it's balanced. So this one is asking about hydrogen. That's the heat released for this reaction per 2 moles of hydrogen. Really important. That is stoichiometry for thermo. All right. That amount of heat is released when 2 moles of hydrogen react. 16 grams is not 2 moles of hydrogen. And I tried to choose easy numbers to help you out here. And I said use 2 grams per mole for the mass of hydrogen. Molar mass of 2 grams, by definition, molar mass, 2 grams per mole for H2. So you can probably do this in your head. If you need to do the calculation, 16 grams of hydrogen, 1 mole is 2 grams of hydrogen, and that will give us 8 moles of hydrogen. All right? So that's important. That's stoichiometry. Not really stoichiometry. That's just using molar mass to go from grams to moles, but we do that a lot in stoichiometry. And now here's kind of the thermostoichiometry piece. This is the heat for 2 moles of hydrogen reacted. We're reacting more. In effect, we're reacting 4 times as much. 8 is 4 times 2. But we can just do a conversion here. 8 moles. And again, you should always double check units. Write your units, please. Moles will cancel. And I don't remember what this comes out to be. I guess I should break out my calculator. It's going to be 571.6 times 4, which looks like it's going to be A, 2,290 or so. Let's see. Yes, it's actually 2,286.4. but rounded to 3 sig figs. So there's 3 sig figs in 16.0 and 2.00. So we're going to round to 3 sig figs. The correct answer is A, 2.29 times 10 to the third. All right, keep cranking along here. So here we have this decomposition of carbon tetrachloride. Okay, right away, your first thought should be, this is going to be a temperature-dependent process. And again, I would just look at this and say, well, to break something apart, we're going to have to add heat, right? Which is what we have to do. So our delta H is endo. So once I see that, once it's endothermic, it's temperature dependent. Now we do lead to an increase in entropy because we go from 1 mole of gas to 1 mole of solid and 2 moles of gas. So that's our positive delta S. So we want to calculate delta G for this. Pretty simple equation. But be careful, units and temperature. Temperature needs to be in Kelvin. Watch your units of delta H and delta S, kilojoules versus joules per Kelvin. We're going to have to take care of that. So delta G, delta H, 95 point, and I wrote over my, I think it's 0.7 kilojoules, minus 298 Kelvin. Delta S is 142.2 joules per Kelvin. All right. And you might be good with conversions and say, oh, right away, I need to divide that by 1,000. But maybe you'll need to write out that we want to get to kilojoules. Kilo means 1,000. Right? Joules will now cancel. And now we have kilojoules. Kelvin cancels as well. Kilojoules minus kilojoules. Now we're good to go. So let me punch this into my calculator, make sure that I get this right. 298 times 142.2 divided by 1,000. So you should get about 42.4 or so for this calculation, but we're subtracting that from 95.7. And that looks like it's going to give us a positive 53.3. So what does that tell you about spontaneity? Yeah, not spontaneous at this temperature. Remember, negative delta G tells us spontaneity. So this is not spontaneous at 25 Celsius. There's just not enough energy to break apart that molecule. We're going to have to raise the temperature. Remember, endothermic, we have to add heat. We're going to have to raise the temperature to put more energy in before we can break that molecule apart. All right, fun stuff. 10. At what temperature will a reaction become spontaneous? So here's another example. The one we just worked was a positive delta H, positive delta S. We talked about how that's going to be temperature dependent. All right, so let's actually see how we would do that calculation. And the way we're going to do that is with that same delta G equation that we just looked at. And as we talked about above, we want to find when delta G becomes negative. Negative delta G indicates spontaneity. Well, an easier assumption than some negative number is just to assume delta G is 0. So then we're right on the borderline there between positive and negative. Makes our calculation much simpler because now I can just add T delta S to both sides. Divide by delta S. And with temperature, it's delta H divided by delta S. Plug in. Be careful of units again. I'm just going to go ahead and convert this to joules, my delta H. Kilo just means 1,000, 10 to the third. Delta S is 411 joules per Kelvin. Joules cancel. 1 over Kelvin, the denominator, is equivalent to temperature in Kelvin. And I end up with 433 Kelvin. Okay? So it's either D or E, because those have 433 Kelvin. So that's cool. So we've narrowed it down to 2. Now, this is where you have to have a little bit more knowledge about, a positive positive situation, which is temperature dependent for delta H and delta S, versus negative delta H, negative delta S. Okay? So at this point, we found out, well, this should become spontaneous at 433. Is it spontaneous? And that's where delta G is 0. So is it now going to be spontaneous above that temperature or below that temperature? And the way I like to think about this is endothermic. Endothermic reactions, we have to add heat. Oh, add heat. Increase the temperature. Increase. So go above 433. All temperatures above 433. Okay? So endothermic reactions are favored by raising the temperature. If we had a situation with delta H negative and delta S negative, okay, this is exothermic. Heat needs to go from the system to the surroundings. We need to get heat out of that system. We can help that by lowering the temperature. We'll help pull heat out of that system. So exothermic reactions are favored by lowering the temperature if they're not spontaneous. Endothermic are favored by raising the temperature. All right. How many have we done? So that's 10, but I skipped 3. So maybe we'll do 3 more here. All right. So now we're getting into kinetics. So all that first material, and again, I skipped 3 of them, which you'll see at the end here. All that first material was thermo. Is a reaction going to be spontaneous? At what temperature will it be spontaneous? All that kind of stuff. Now we're into reaction rates. So this is giving us the rate at which bromine is being produced, or the rate of appearance, the production of bromine. We want to know at what rate is the reactant disappearing or reacting. And your coefficients are going to play a role in this. Okay? This one might be easy enough for you to see. It's a simple mole ratio. But let's look at how we would set this up. So our rate is 0.8 moles of bromine per liter per second. And we want to get to the rate for NO2Br, so moles per liter per second. So this is really just a stoichiometry problem. We have to convert from moles of bromine to moles of NO2Br. We know how to convert from moles to moles, right? Yeah, we just need the mole ratio, 2 to 1. Boom. 2 moles of NO2Br for 1 mole of Br2. Again, write your units, because then you can see that moles of Br2 cancel if you set it up correctly, and we're going to end up with 1.6, which on this version is choice E. Okay? So the rate will depend on what we're looking at in that reaction. Okay? Because of that coefficient of 2, that reactant is reacting twice as fast as we are producing Br2, bromine. Now you might be thinking, shouldn't the amount of the reactant be decreasing with time? And the answer is yes. So why isn't there a negative sign? There's your answer. We've already taken care of the negative sign. It's already indicating that the reactant is reacting. It's disappearing. You're not going to have a negative amount of the reactant disappear. Okay, that negative sign is just telling you direction. Okay, is that amount decreasing or is it increasing? But the amount is a real amount. It's not a negative amount. Hope that kind of makes sense. All right, I think everybody did really well on this one. We spent a lot of time talking about what factors affect reaction rate, and there's a lot of things that affect reaction rate, and all of these do. Concentration of reactant. Remember the rate law, that has concentration in it. Okay, concentration certainly affects rate. Temperature, reactions speed up as you raise the temperature because things are going to collide with more energy. How many collisions you have. More collisions, faster rate. Activation energy is really important. That's the energy you have to put in to start that reaction. If that energy is small, the reaction is going to be faster. If that energy is larger, the reaction is going to be slower. That will certainly affect rate. And we did talk about that molecules must be oriented right so the right things come together when they react. Okay? All of these things affect the rate of a reaction. All right, I have a page break here because I've added more space in the, there we go. All right, 13. I thought I did 13 as one of the 5 most missed, but I think that was 15. So let's do 13. Okay, so here you are essentially told the rate law in words. Okay, you're given the rate law in words. All right, so let's write that out. Rate, again, the rate law always has this form. Rate is equal to a rate constant, and it says it's first order with respect to A, and it's first order with respect to B. Okay, now remember, in general, we cannot write the rate law from the balanced equation. So don't look at that coefficient and think that A needs to be 2. So now we're going to see what will change the rate. Okay, what will change this? What if I increase the concentration of A? So just mathematically look at that. If I increase A, yeah, the rate's going to increase as well. What if I decrease the concentration of B? Yeah, the rate's going to then decrease. If I decrease this number, the rate will decrease. What about temperature? Yeah, we just talked about in problem 12, temperature is one of the things that certainly affects reaction rate. Higher temperature, faster rate. Lower temperature, slower rate. All right, now, what about the last one? The rate is measured again after the reaction has run for a while. Well, what's going to happen to our concentrations after that reaction has run for a while? Yeah, these concentrations, and let me erase here, after we let that reaction run for a while, the concentration of A has decreased, concentration of B has decreased. So we've, in effect, decreased both of those concentrations. What's that going to do to the rate? Yeah, it's going to decrease the rate. Okay. Wow, all 4. All right, so think about that. Remember how we talked about that a plot typically of concentration, let's just choose A at this point, versus time, going to be a curve. And that's because as the reaction runs, reactant concentrations decrease, reaction slows down. It's going to be fast initially, high concentration, slows down as concentration drops off. All right, you know what? I think I'm going to leave it there. Just because I'm at work, it's getting close to 5 o'clock. I want to wrap this up, get home. But this will essentially get us through, let's see, I got through 13. 15 was in the most missed, and then also 24. So that looks like about 15 of the problems so far out of the 24. That'll give you a good start if you want to start studying Friday night. And then on Saturday, tomorrow, I will record the remaining 9 and post that. All right. I hope this helps. Hopes it helps you with the thought process of thinking through these types of problems. Again, the retest will be the same material, but different problems. So restudy, make sure you're prepared. All right. I will see you maybe Monday night for the retest at 8 p.m. in our normal classroom. See you soon.